When Charles Darwin came up with this theory of evolution, he didn't know anything about genetics. Remember, Gregor Mendel lived and worked kind of around the same time as him, and he definitely didn't know anything about DNA because Rosalind Franklin and Watson and Crick didn't make their discoveries to close to 100 years after he published The Origin of Species. Now, today we do know a lot more about genetics, and the ideas of genetics can really help sort of fortify the idea that evolution happens. And so we're going to start talking about how we can track evolution. How can we track changes that happen in a population by looking at the genes that are available in a population, or more specifically, something called gene pool. Some background information we have to remember about populations. Remember, populations are the groups of one kind of organism that lives in one area. So it's not all the frogs of the world, but it's one particular species of frog that maybe lives in one pond. So if you look at this picture here, we've got a frog population. Evolution can't happen unless there's some sort of variations that are in a population. And in this particular frog population, kind of silly looking one, most of the frogs are green, but there are some other options for skin color. There's a couple that are purple and one that is red. So where do sources of variation come from? Most variation comes from mutation. In fact, the only way we ever get new traits is from mutations or changes that happen to DNA. But don't forget, mutations aren't always good. Sometimes mutations actually have no effect on an organism, and sometimes they have bad effects. So mutations aren't always just sources of good things to happen. One of the other sources of genetic variation is sex. Organisms that don't reproduce sexually actually are less likely to show new variety from one generation to the next. Humans, because you have two parents that sort of had to combine some of their genes in order to make you, you are not identical to either of your parents. If humans had reproduced asexually, you would only have one parent and you would look identical to them. So it's a good thing that we do have sexual reproduction so we can get all kinds of new combinations of genes. So let's talk about something called the gene pool. Now, the technical definition of a gene pool is all the alleles that occur in one population. So, for example, we've got these warthogs right here. Some of them can be sort of that darker blackish brown color, and some of them are lighter brown color. But just looking at phenotypes doesn't tell us enough about organisms from one generation to the next. What we really want to know is what are the available genes that are out there for them. And so in the case of the warthogs, what we're looking at is how many big B's are there and how many little B's are there. So we're going to need to calculate something called allele frequency. Allele frequency is how often do we see one allele in the gene pool? Or in other words, how often do we see big B's and how often do we see little b's in all the organisms that live in that area? And of course, there's a nice little mathematical equation that we can use where we would take how many of the one type of allele do we have, like a big B, and divide it by the total number of alleles that are in that population. Not as helpful from an evolutionary standpoint, but something that we kind of do usually end up looking at a little bit is looking at the phenotypic frequencies of organisms in an environment. And that's how often do we see a particular phenotype. So how many of those warthogs are black and how many of them are brown? And, we can just get a sort of a percentage there. And same thing, we've got the same kind of mathematical equation that we can use. But I think it's easier if we actually just take a look at a population and see how to do these calculations. So first, let's take a look at this population of flowers here. It's pretty easy. There's only 5 flowers here, and they all seem to have the same phenotype. So if we were to count up, there are 5 flowers and all 5 of them are black. If we were to do our phenotypic frequencies, we can see that 5 out of 5 of the flowers are black and 0 out of the 5 of the flowers are gray. So we have 100% black, 0% gray. But we know that allele frequencies are actually going to give us a little bit better idea of what's going on in this population. So let's look at the allele frequencies. If you were to count the number of R's, of capital R's, versus the number of little r's in this population, you should have twice as many alleles as you do phenotypes, because remember, every organism has 2 alleles for every trait that they show. So let's count. How many capital R's are there? The first flower has 2. Second flower has 2, so that's 4. Next flower has 1 more, that's 5, 6, and then 7. So the 7 of these alleles are capital R out of the 10 possible, which gives us 70% capital R, or the black allele. And then for the lowercase r's, we would just count up how many there are, and there's 3. Same thing out of the 10 possible. And so we've got 3 out of 10 of the alleles, or 30% of the alleles, are lowercase r. Now this gives us a lot better idea of that we could possibly expect in the next generation. In the next generation, we could have all black flowers, and evolution maybe wouldn't have happened, but we could also have maybe 1 or 2 gray flowers and evolution wouldn't have happened either. It just depends on which alleles get passed on with which frequency to the next generation. So if our allele frequencies stay the same from one generation to the next, about 70% capital R and about 30% lowercase r, evolution doesn't happen, even though maybe the phenotypes have changed slightly. Let's take a look at a second population. So here's our second flower population. Once again, we still have 5 flowers, but you notice that there's a little bit more variety in this population. So here we have, I want you to try to see if you can figure out the phenotypic frequency first. So how many of the flowers are black? How many of them are gray? And write it down on your paper. What you should have found was that 3 out of 5 of the flowers are black. That's about 60% of the flowers are black. And that 2 out of 5 of the flowers are gray, about 40%. Let's look at the allele frequencies. Count up how many capital R's we have in this population, how many lowercase r's we have in this population. What you should find is that there are 5 capital R's out of the total number of R's. So we have about 50% of this population has capital R. And same thing, about 50% of this population is lowercase r for our allele frequencies. So you notice phenotype frequencies and allele frequencies don't always match up. Now that we know a little bit more about gene pools and evolution, what we can kind of redefine evolution as being is evolution is really just some sort of change that happens in the allele frequency of a gene pool. And if you look at this picture of the flowers from one generation to the next, you can see that the number of lowercase r's has actually decreased. And so that's how we know evolution has happened, is if there's actual changes in the alleles that are possible in a population. We've been talking about some of the things that can cause evolution, but not quite all of them. So let's talk about sort of the 5 main categories of things that can cause changes in the gene pool. In other words, evolution. The first one is something we do know about, mutations. Remember, mutations can bring new alleles into a gene pool, which could, affect evolution and cause there to be some changes in a gene pool. Secondly, of course, there's natural selection. We've spent a lot of time talking about that. We do know that nature chooses some traits that make it more likely for an organism to survive and reproduce. So we will see some traits that become more common simply because they make that organism more likely to survive in the environment that they live in. A third thing that we haven't talked too much about yet is that of sexual selection. In sexual selection, some traits are chosen that make an individual more desirable, usually to the ladies. And so sometimes there are traits that you would think would be bad from a natural selection standpoint, but actually turn out to keep increasing from generation to generation simply because they make you more attractive to somebody from the opposite sex. So take a look at these peacocks that are on the video here. You see the female down the bottom. She's kind of plain, not that impressive looking, but the male, he's got these beautiful feathers. And it turns out that lady peacocks will only mate with men who have male peacocks who have humongous, beautiful, healthy looking feathers. And so even though having those giant feathers is not good from a natural selection standpoint, because those guys, think about how hard it would be to run away from predators and to stay hidden when you've got all these crazy fancy feathers. The numbers of male peacocks with these kind of feather plumages will increase from one generation to the next simply because females find it so attractive. Another new concept is that of gene flow. And gene flow would be when an organism from one population leaves where they are and goes and joins another population. So if you're to think about even the deer that live in the forest reserves in this area of Orland Park, if they were to leave this area and to travel to, head a little bit further north into some other areas, some other forest reserve areas, maybe looking for a mate or maybe looking for some more food, they might carry traits into that population that wouldn't have been there before. And so we can see that sometimes alleles that weren't in a certain population may appear there or may disappear from a population simply because of immigration or emigration. And then the final thing is the idea of genetic drift. And genetic drift is that sometimes random events happen and certain alleles just increase or decrease in a population not because it made them more likely to survive or reproduce or anything, but just simply random events. And, maybe certain alleles may disappear just because of a storm or something random that really happens. Or sometimes, there's other things that can happen that you can see in this picture. We've got somebody just sort of squishing a couple of the green bugs, and now there's less of them the next generation. Genetic drift is most likely to affect very small populations. Large populations aren't as subject to genetic drift, but we do see in small populations that sometimes evolution happens simply because of random things that can happen. Now, we're going to be spending a lot more time talking about all of these concepts in the coming days. Thank you.